Hey everyone. In this video, we're going to look at how we evaluate competing scientific models of physical phenomenon. But before we get into that, let's look at some of the key things that are required for a scientific model in general. So if I have some proposed scientific models, they have to be based on observation and experiment. We look for patterns in experimental and observational data, and we try to characterize and quantify these patterns so we can use them to interpolate between data points, extrapolate to find new data points, and be able to make testable predictions. Now, in some cases, we might have some set of previously identified scientific models, and we want to develop a mathematical framework that links multiple different patterns together. Some examples of this are Newton's laws of motion, linking together motions that were identified on the Earth and motions that were identified in the planets. Another good example would be Maxwell's equations for electromagnetism, which expanded and linked together the work of many scientists like Coulomb, Gauss, Faraday, Ampere, and took all of the experiments that they had done on electricity and magnetism and linked them together and found a single unifying framework that describes everything that we have about classical magnetism, electricity, and light. The development of these mathematical frameworks to link these ideas was still based on those previously experimentally verified models. So even though it's more mathematical and theoretical in nature, those underpinnings are still based on observation and experiments. Okay. These models have to be able to make testable predictions that are falsifiable. In the last video in this series, we talked about how these ideas of being able to make specific predictions and falsifiability are closely linked together. The more specific the prediction that I can try to make, the greater the opportunity we have for that model to be falsified. And it's important to remember that we can never absolutely prove any of our models to be correct, because that would take exhaustive knowledge testing it under every single condition at every single place in the universe for all time. We can't really do that. We can only give them as many opportunities to be falsified as possible. So again, it's better if these models make specific, quantifiable predictions. And this is why mathematical models become so useful. If I have an experiment where I'm dropping objects from different heights, I might find a pattern of saying, well, the higher up I drop the object from, the longer it's going to take to hit the ground. But we want to be more specific. How much longer is it taking? If I double the height, do I double the fall time, or do I quadruple the fall time, or what happens to that fall time? It should actually be, as you go to greater heights, the fall time should increase with the square root of the height, but we'll leave those details for another one of the testing physics series. But again, this is why we ideally want to describe these models with math so they make as specific predictions as possible. We also want our models to generally make as few assumptions as possible. And when we do make assumptions, we want to clearly delineate what those assumptions actually are. So those assumptions, we can try to test and potentially falsify those assumptions. For example, Einstein's theory of special relativity, what happens when you're moving closer to the speed of light, is based on two assumptions. One, that the speed of light is independent of how fast the source is moving. Again, this is something that we can try to test and see if there are errors in this assumption, but that's our first assumption. And the second assumption is that if I have an experiment in some inertial reference frame, then whichever inertial reference frame it is, I should get the same experiment. An experiment that's at rest should have the same results as an experiment where the entire apparatus is moving to the side at a constant velocity. So again, when we have assumptions, we want to make as few assumptions as possible. You can also relate this to Occam's razor. We don't want to multiply entities unnecessarily. We don't want to make more assumptions than we have to in our model. And again, when we do have to make those assumptions, because we have to start somewhere, we want to clearly delineate what those assumptions are so we can try to put them to the test as well. And we also want to identify what is the range of applicability for this particular model. Is it only valid under certain conditions? Is it a universal law where it's always going to be assumed? We want to clearly identify under what conditions is this valid. So let's say I've got two models, and hopefully these two models meet at least these conditions to a reasonable degree. So let's suppose I have two proposed models for some kind of physical phenomenon. If I want to try to compare those two models with each other, see which one is more accurate, which one is the more reliable model, we have to find observational or experimental situations where those two models make different predictions. Okay? For example, let's say I have two models. We'll just call them Model 1 and Model 2, and these are to look at some kind of physical phenomenon. And let's say if I set up a certain kind of experimental conditions, we'll call this condition A, Model 1 predicts that the outcome will be X, and Model 2 also agrees that outcome will be X. Okay. Well, this set of experimental conditions, since both models are making the same prediction, this particular experiment isn't very good at distinguishing which of those models is more accurate, or at least which of those models can we throw out. Because remember, we can't verify absolutely anything in science. That would take exhaustive knowledge. But we can try to eliminate options by falsifying them. So this, well, I can't really distinguish which of these models is better than the other because they both make the same predictions under these circumstances. But what if I have another set of experimental conditions, and this one, let's say experimental condition B, Model 1 predicts that Y should happen, and under the same conditions, Model 2 predicts that Z should happen. Okay. These are now making different predictions. So if I run experiment B, set it up in a particular way where these two models make different predictions on what should happen, well, then I could potentially distinguish between these two models. I can identify if one or both of them are wrong by testing out this specific experimental condition. So again, when we're trying to compare two different models, we want to look for cases where they make different predictions on how some experiment should run. And then we run that experiment and let the data from that experiment identify which of these models is more reliable. We don't use the models to, say, oh, this experiment was working or this experiment wasn't working. We have these two models and we use the experiment to distinguish which of those models is meeting its criteria for making testable predictions and having those predictions be accurate to reality. Let's look at a particular case of this. Let's try looking at the Ptolemaic versus the Copernican models of the solar system. So the Ptolemaic was the old Earth-centered model where the Earth is at the center of the solar system and everything else orbits around the Earth. Okay. Now, there's a couple of points to this that I want to kind of highlight. There are a number of different correction terms that were introduced to this Ptolemaic model so that the predictions of this Ptolemaic model matched observations of how stars move across the sky, how the sun moves across the sky, how the different planets move across different parts of the sky in different ways. So, for example, the planets orbit on these little epicycles. So the planets, instead of just orbiting the Earth, they also have these little circles that are called epicycles. And for Mercury and Venus, those epicycles are kind of locked in front of the sun. So if this system rotates, so let me draw this part. If we have the Earth over here, and this system rotates, if the sun has rotated into this position, Mercury and Venus on their epicycles will always be directly in line with the sun. And this means that Mercury and Venus will never get very far away from the sun. You'll never see the sun in this direction and then Venus, say, far over in this direction. Okay. Now, for the outer planets are also going on their epicycles. They're moving around the Earth, not locked in with the sun, so they can be on different sides of the sky than the sun. But these epicycles were also introduced so that scientists at the time could explain what we call retrograde motion. Retrograde motion is where most of the time a planet will move in the same direction across the sky, but every once in a while it'll turn back and then turn back again and keep going in the same direction that it was before. So this motion right in here, this is our retrograde motion, where that planet momentarily goes backwards from the way that it normally moves. These epicycles were introduced so as the planet is orbiting around the Earth, the motion of that matchup between the motion of the epicycle and the motion of the center of that epicycle around the Earth gives kind of this spiraling motion. So most of the time, the planet's going in the same direction across the sky, but every once in a while there's a little backtracking motion. That's what those epicycles were trying to explain. Okay. So this Ptolemaic model actually did a fairly good job with all of these kind of correction terms added into it to accurately be able to describe how the planets move across the sky. Okay. So that's our Ptolemaic Earth-centered model. We've also got the Copernican or sun-centered model. This is the one that we should hopefully be more familiar with, where the sun is at the center of the solar system, or at least very near to the center of mass of the solar system, and all of the planets, including the Earth, orbit around the sun. We want to look at these two models and figure out where do they make specific predictions, and is there anywhere where they make different predictions on some kind of observation. So let's look at these two models in a little bit more detail. When we look at how they describe the motion of the planets compared to background stars, they both match up pretty well. In fact, the Ptolemaic model, when Copernicus was kind of going through his observations for this, the Ptolemaic model with these epicycles was actually a little bit better at being able to make these very, very specific predictions. All of these little correction terms, these epicycles, these added in features like the equipoint and the different that basically describes, adds in a motion of the Earth around some other point that corrects for how the sun doesn't always move the same speed across the sky at different points of the year. All of those correction terms allowed the Ptolemaic model to make very, very accurate predictions on how these planets would move. And even when other errors were found, extra little epicycles were added to keep on adding these little correction terms. So with all of those correction terms kind of somewhat artificially put in, the Ptolemaic model was very accurate at predicting the motions of the planets compared to background stars, whereas the Copernican model, which was still assuming at the time that all of these orbits were circular orbits rather than the ellipses that we now know they are, was still not quite as finely tuned as the other one. Okay. So they both did a fairly good job of describing the motion of planets compared to background stars, even though they have these two very, very different models. Again, both are able to explain things like why we never see Mercury and Venus very far from the sun. For the Ptolemaic model, it's because Mercury and Venus would be going on these epicycles that are kind of locked in place, aligned with the sun. So that's why we never see Mercury, Venus in some complete other area of the sky. Whereas in the Copernican model, Mercury and Venus would be in orbits inside of the Earth's orbit, so we're never going to see Venus any further away from the sun than that. We're never going to see Venus in this direction compared to the direction to the sun. The Copernican model can also explain things like retrograde motion. So if I have a couple of points, let me label a couple of points on here. Let's say this is 1, 2, 3, 4, and 5. 2, 3, 4, and 5. And let's say one of the outer planets is going through this kind of motion. 1, 2, 3. Let me get that 2 a little bit. These should be equally spaced, but the further out the planet is, the slower it orbits. So in this case, when we're matching up these orbits, we're going to say, well, I see an object over here. I now see this object in front of this star, so that would be 1, that would be 2. I now see the planet in front of this star, so this would be 3. And then over here for 4. And over here for 5. I guess I added an extra star there that I didn't need. But we have this 1, 2, 3, 4, 5 kind of motion. The Copernican model is also able to explain that retrograde motion. The point I'm trying to make here is that both of these models seem to be able to explain the general motion of these planets compared to the background stars to higher or lower accuracy. Okay. So we need some new kind of observation that is able to distinguish between what these two models predict. Okay. And this comes from looking at the phases of Venus. Okay. If we go back here, if Venus is entirely in front of the sun, when we look at what parts of Venus would be illuminated by the sun and what parts of that planet we can see from the Earth, we're never going to be able to see more than a crescent. Okay? So let's say here's the Earth, here's Venus going through its epicycle, and the sun is on the far side. If that's what's happening, we would never be able to see more than just a thin crescent for Venus's phases. We could also adjust this and say, well, what if Venus was entirely outside, was going on an epicycle completely outside, but still lined up with the sun like that? Well, then we'd never see new moon phases, or I guess new Venus phases. We'd never see cases where the majority of it is in shadow. We just see phases where most of the visible surface is illuminated from our perspective. Okay. So the phases of Venus, the Ptolemaic model makes some very specific predictions. Whereas the Copernican model, if I have the Earth, let me see if I've got another version of this down here. Yep. So if Venus is orbiting around the sun, and we're on the Earth and outside of Venus's orbit, then we should see the full set of phases. You know, sometimes where we only see the unlit side of Venus, sometimes where if Venus were at this position over here, we'd see the left half of Venus being illuminated and the right half in shadow, so that would be this phase over here. If Venus is at this part in its orbit, we should see the entire visible surface of Venus being illuminated. We would get that full set of different phases. So this is where the Ptolemaic and the Copernican model make different predictions. And those are the kind of predictions that we want to test. And when Galileo took his early telescope and aimed it at Venus, these are some of the pictures that he drew representing the different phases of Venus that he saw at different times of the year as Venus moved around in its orbit. And he identified all of these different phases. It matched with the Copernican model and disproved the Ptolemaic model. So this is an example of how we want, if we're testing a couple of different hypotheses, we want to test them under conditions where those two models, those two hypotheses, make different predictions about the outcome of some observation or the outcome of some experiment. Now, a couple other just quick points about this Ptolemaic versus Copernican model. As I said, the Copernican model, it wasn't quite as good at describing the motion of the planets as the Ptolemaic model was, because the Copernican model was still assuming that all of these orbits were circular, when we now know that they're ellipses. And the Ptolemaic model had all of these extra little correction effects added in. So at least at the beginning, before the Copernican model had been properly, I guess you could say, calibrated, the Ptolemaic model was still a little bit better at predicting the motion of planets compared to background stars. Another thing that was kind of interesting is that in the Copernican model, if you have the sun at the center of the Copernican model and the Earth orbiting around it, then other stars, objects further away, as the Earth orbits, the argument was that relatively nearby stars, we should see a little bit of an apparent change in their position compared to other background stars, what we call the parallax effect, due to the motion of the Earth around the sun. Okay. But at the time, no such observation could be made. And the argument was, well, that is a point against the Copernican model, unless those other stars are just so ridiculously far away that we don't have the technology to actually detect those tiny little parallax effects. Well, it turns out that all the other stars, compared to everything else in the solar system, other stars are really, really far away. And it wasn't until, I think, the mid to late 1800s where we actually had the technology to actually be able to measure those small parallax effects. Again, when we're trying to test these different models and see under what experimental conditions we get these different predictions to distinguish between these models, one of the interesting aspects is when do we have the technology and the ability to actually experimentally test these conditions? This distinguishing what are the phases of Venus, we couldn't actually do that until we had a moderately good telescope, until we had Galileo's early telescope. We did not have the technology to distinguish which of these two models was correct. Okay? With the effect of parallax, for stellar parallax, the Earth orbits around the sun, well, near stars that are closer by, we should see this parallax shift on the sky. In the time of Copernicus, we did not have the technology to do that. We only got that technology in, again, the mid to late 1800s, if I'm remembering correctly. So there's definitely something to be said about how our technological abilities are very, very closely linked to what kind of models we can actually test, what are our abilities to test these models. One of the kind of modern equivalents to this is when scientists are trying to look at extensions of the standard model of particle physics. The standard model of particle physics is basically a summary of everything that we know about how particles work, like quarks, electrons, different kinds of subatomic particles, all of these different things that we get from particle physics experiments is kind of summarized in what we call the standard model. But different groups are looking for extensions of the standard model. Are there particles that we haven't detected yet? And could these be associated with things like dark matter or dark energy? Well, the problem is, with some of these models, we don't yet have the ability to experimentally test some of these conditions, especially when you get into extensions of the standard model along the lines of string theory. String theory, some of those differences where we would actually see a difference from the standard model require phenomenally high energies, and we simply don't have the technology to be able to test those. So this is a limitation on things like string theory, extensions of the standard model, where we don't have the ability to actually put those, to test the conditions where those models would make different kinds of predictions. Another thing, whenever we're describing these models, we want to see, are there independent lines of evidence available? We don't want to base all of our conclusions off of a single experiment, though with a model, if a single experiment directly contradicts the prediction of your model, that model must be revised or discarded. We're definitely going to go into more detail in a future video talking about how do we establish these models in the first place, how do we gather data, how do we make sure that it's not just a false signal, just something that happened by chance, going into some of the things on burden of proof. Those will definitely be in future videos. But ideally, we want a set of different experiments that use different methods of testing the predictions of this model, or different aspects of the predictions of these models. So that's another thing that you want to consider when comparing different models. But it is still important to remember that even a single experiment that directly contradicts the prediction of that model has to be either significantly revised or discarded. We don't really want to prove or say that we have a huge amount of confidence if it's only based on one experiment, but we can falsify it based on one experiment. And one other thing, and this is kind of getting into extensions of the standard model and string theory, are there too many fit parameters for the model to be falsifiable? This kind of goes back to we want to make as few assumptions as possible. With extensions of the standard model, if I can just keep adding on new kinds of particles with new kinds of properties, there are so many different ways that I could set up those particles that it starts to get into the range where I'm not sure if this model or this approach is necessarily falsifiable. Because if I do an experiment and it doesn't match my data, well, maybe I can just change the properties of my proposed particle to match with that data. That's not necessarily a particularly great way of doing science, because we want to have our models be falsifiable. If it has too many assumptions that are just introduced into it, or if it has too narrow a range of applicability, so it's only applicable under a very, very specific set of circumstances, then that's not ideal. We've got kind of a bit of a problem there. So again, the main thing that I wanted to highlight with this video is that if I have two models and I want to test out which model is more accurate, I have to base that on experimental data, and I have to find an experiment where those two models make different predictions, and then test it under those conditions, and then see, well, what does nature, what does experiment and observation and reality say about which of these models is successful at the goal of making testable predictions. So that's it for this video. As always, thank you for the view. If you have questions, throw them into the comments below. If you're commenting, make sure you're being respectful and to other people. And see you in the next video.